Welcome to another video where we'll have a look at solving the exercise 16.6.2 pilot chamber 2. Let's make the drawing and see what the system we are looking at looked like. So the system that we have a supply pressure, some cells which we can vary over time. We have an orifice, we have a chamber, we have another orifice, and then we have the tank connection. So I have defined the flow in this direction and giving it a name. It's named like from supply to the chamber and from the chamber to the tank. And let's later on have a look at what could this chamber be like when we have done the exercise. The first thing we're asked to do in question A and B, that is to calculate or set up a model for the flow going in and out of this chamber. And we should remember that the pressure everywhere and so on could be time changing. So first of all, the QSC pressure flow. So I have the discharge coefficient, the area, opening area of the orifice up here, the density of the fluid, the pressure, and the pressure. I use the absolute value in here because if I have a higher pressure in my chamber than I have out here, well, I'll have a negative number having imaginary solutions. So, and then out here I take the sign of the pressure drop. So you could say that this first part of the equation gives me the amount of flow, and the second part here gives me the direction of the flow. Now the flow out of the chamber to the tank, what is that? So these two orifice equations give me the flow in and out. And of course we should recall that our pressure and flows, they could be are depending on time in our system. Down here I omit the parentheses on the time indicator just to save some space. So the third question that we are asked is to set up a model for the pressure in here. How is that changing? How can we model that? And for that we use the continuity equation. And in our system, we have the change in volume over time. Well, we have a fixed volume, so that's 0. And often when we want to set up models, we want to isolate for the derivative of the parameter that we're trying to model. And having the model, it's always nice to do a small sanity check. If the flow in is larger than the flow out, what will happen with the pressure? Well, it will increase. How much it is increasing, that depends on the stiffness of the oil or the bulk modulus of the oil and the volume that we have. How big is that volume? So this is, we could say that is our time domain model for the system that we have up here. All right, let's start linearizing the orifice equation for the flow into the chamber. And when we do the linearization, we use first order Taylor approximation. So in the first order Taylor approximation, we have that our approximation of the flow, that is equal to the flow at some linearization point Let's put this small sign up here so that we can see that's the approximation by the first order Taylor approximation. So we take the value of our system at the linearization point, we take the partial derivative with respect to each of the parameters as we know, and then we multiply with the change away from the linearization point. As we know, this is not a linear model, so we make it into change variables, subtracting this linearization point value from here, and then saying this is our new parameters that we're working with. So here we have our linear model. What we should know now is that this KQP, that is the partial derivative with respect to PS at our linearization points. So when we had taken the partial derivative, we put in our linearization point values. And we can see that up here I use the same partial derivative as here, only the difference is now I use the minus instead of the plus. And that's what we have due to the difference in the signs in here. So my linear model for the flow in is here. And let's put on a small 1 here so that we know that is for orifice 1. And the linear model for the flow from the chamber to the tank, we can put that up in the same way. Only difference is now that the KQ2 is the partial derivative of our flow out of the chamber with respect to the pressure inside the chamber. And then finally we have continuity equation, but with the assumption of a constant bulk modulus as we have in this exercise and a constant volume. Well, that is already a linear model. We can put it up in change variable settings like the one that we have here if we want to, but it is already a linear model. So the linear equations that we have is the one up here, here, and here. That is our linear model. So we have the time domain model with these two and the later one down here. That is our time domain nonlinear model, and here we have a time domain linear model. Now with a bit of space left over here, let's take the Laplace transform of the different ones that we have. And what we do is we say that we have now transformed them into the Laplace domain, and will look like this. So that is the two orifice equations, quite straightforward. Continuity equation, and here we'll have an S coming out of the differential term being Laplace transformed, and we will assume that the initial condition is 0 so that we don't have this extra term that comes on in the Laplace domain. Now we have the three equations. Let's take the two top one, plug that in the last one, and then let's take this hydraulic capacitance and move that to the left side of the equation. So we see that we have terms here with supply pressure, tank pressure, and then the chamber pressure. Let's pull these two with the chamber pressure to the left side, so we have that all on one side of the equation. Here we have now gathered all the terms with the chamber pressure, which is the one that we want to find out how is that changing depending on how do we change the systems out here. And now as you see, we have two different inputs that we can use in the system. And doing a transfer function, we have a bit of an issue having two inputs. So doing a transfer function, we need to say one of them is 0 or constant while changing the other one, and then we can swap around. In the system like this, often the tank pressure could be set to 0 or maybe not changing. So what we'll do is try to set this later part to be 0. And then we will set up the transfer function where we have the supply pressure as input and the chamber pressure as output. So up here we now have the transfer function. It's pretty easy to see that we have a first order transfer function. So some kind of a low pass filter is what we have designed. And if we compare it to the other exercise that we had with pilot chamber 1, now we see that we have 2 terms down here. So that also gives us that the DC gain of this system depends on the orifices that we have here and the partial derivative of that. And that is something to do with what is the size of the orifice, what is the opening area that we have. So this will be our DC gain for that system. And we can see that we can change the time constant both by changing these values here, the size of the orifice, or we can change the size of the volume. A system like this, where do we have that? It could sit in a pump control loop. So if you have a variable displacement pump, the pressure line comes out here, is fit into some kind of a valve that again goes into the cylinder moving the system. And here you could have a pilot line. Maybe we even have another pilot line over here at the other side, going from this in here. And if we don't want the pressure pulsations that we have here to go directly into this valve, well, then we can put on a small orifice here. Could be that we have a bleed off orifice to another point. So in a system like this, or in another valve that is controlled by a pilot pressure, that's a place where we can see this. And if we have some issues with this being unstable, it could be that the fixes change the area of our valve that we have, the small orifices that we have put in to the system. So we have these kind of systems all over in our hydraulic systems. When we want to stabilize and then have a low pass filtering of a pressure in the system, this is the way that you can do it.